Okay. It works now? Um, I think it works. Okay, thank you. And as I said, I joined UB this year, and my research is on seismic hazard risk modeling, so related but not exactly the material of this class. And in general, there is a structure of like material that I'm thinking is appropriate to follow, but I also want to understand from you what are the topics that are most useful so that we can focus. So if you have any suggestions on any topics that may be more applicable for the type of research you are doing or the types of project that you are going to encounter, please let me know and we can tailor the schedule and the class accordingly. Um, So what we will cover is first we will start with some introductory review of seismology, covering tectonics, different seismic sources, how we describe earthquakes in seismology based on their magnitude and other parameters that describe them. And then we will provide an overview of a general overview of the field of geotechnical earthquake engineering, covering a number of subjects, characterizing ground motion, uh, geotechnical or earthquake-induced hazards, and wave propagation and site amplification. Um, I don't have a required textbook for the class. There are some good references that I would leave it up to you if you want to like rent them from the library, or I think some of them are also available online. And like we are not going to strictly follow a textbook, and I know they are expensive, so I will leave it up to your discretion to decide which references and how many of them you want to follow. We will be more closely following the textbooks by Steve Kramer and the second edition by Steve Kramer and John Stewart. And I think they are available, copies of them are available through the library, so you may consider loaning them, or if this is a subject that you want to spend more time, even like it's a good investment. And I also provide some additional references. The Lay and Wallace is more on seismology, if someone is more interested in that. And then there is another book on geotechnical earthquake engineering by Tohata, written in 2008, that is also um, related to what we are going to cover. In terms of the plan, so today we'll see how it will go, but it's mainly an introduction, understanding what the class is going to cover, and maybe even go into some aspects of seismology. Then we will go through the seismology, plate tectonics, how to describe shaking, characterizing ground motions, and how to perform seismic hazard analysis to quantify the level of seismic hazard for different regions and the different methods that we can do, what are their strengths, what are their limitation. Then some advanced topics on seismic hazard that are more related to ongoing research and like what are the open questions and how we are trying to address them. We will spend a class on time series processing and how to select time series for dynamic analysis, or how we can modify them if we don't have good time histories that recorded time histories. Wave propagation and site amplification, understanding how ground motion near the surface or in basins is amplified and how that can create higher demands in our structure. And then we will go through a number of earthquake-induced geohazards, first covering soil properties and understanding how soil properties may change based on the dynamic loading. And then different types of geohazards, such as surface fault rupture, where we have tectonic deformation imposing additional stress in our structure, liquefaction, slope stability, then see how this is covered in seismic design, AC 722 as an example, and depending on how the schedule goes, we can also devote a class or two in advanced topics. And in terms of prerequisites, I don't think that there are any strong prerequisites, but in general, understanding of soil mechanics would be helpful, and some familiarity with geology, structural dynamics, programming can also be helpful, like in helping you with both the background material and programming here, for example, if some of the assignments you want to code them instead of like doing them in Excel or by hand. And for grading, again, we can see how we are progressing, but I'm thinking there will be approximately 5 projects/assignments. It's fine to like you can work as groups or as you fit. The goal here is to learn, but what I want to achieve through that is making sure that you understand the material. So even if you work as groups, please ensure that like it's not someone else helping you and you just write down the answers, but actually you are understanding what is going on. I believe we will have. I don't know the exact date for the midterm, but I'm thinking 1 meter may be reasonable and like spanning, like covering these subjects. And again, I'm flexible. I think like a take-home midterm would be reasonable. And then a final exam, which we can also decide whether it will be in class or take home. And then there will be 10% credit on participation. And in general, because I want to structure this as a graduate class, but also like as a seminar where we can be more interactive and attack things collectively and discuss things. So please participate, ask questions, and in general, please share your input. Okay. So before we go into the subject, I think maybe we can go around and each of us introduce ourselves, like what's our name, like our title, and maybe if we are doing research or any interest that we have. So I already introduced myself, but I will do it again. As I said, my name is Greg Lavrentiadis. I'm an assistant professor here. I started this year. My research is on, I'm part of the geotechnical program here, and my research is on earthquakes, and in particular, characterizing risk and hazard from earthquake-induced hazards. And there, what I want to, like, my focus is on data-driven methods, understanding how to better capture correlation and how to more accurately characterize these hazards so that we can make better risk-informed decisions. So maybe you can continue, George.
Awesome. I'm George Rek. I'm a grad student here, and I'm going to be doing research for you this semester. What else do I need to pick?
Whatever else you think it's.
My favorite color is green.
Okay. Yes.
I'm Chris Cantor. This is my second semester here. And I'm looking forward to doing research with you this summer. And I figured
Hi everyone, I'm Sherry, and this is my first semester at UB. I'm a master's student, and my favorite color is pink.
Hello everyone, I am Abhay Bansal and I am a second year PhD student here. And my research is also in earthquake engineering and dynamics related applications.
And favorite color?
My favorite color is blue.
Blue, okay.
Hi everyone, my name is Sai Teja. I'm doing my master's in transportation engineering. This is my second semester. My favorite color is blue.
Okay. What made you choose this class from transportations?
This one.
Huh?
I'm just starting.
Okay.
Hi everyone, I'm Amino.
We are third year PhD student. My research is on understanding the reinforced concrete structures damaged under the vaccine.
Okay, thank you.
I'm Simon, and I'm an important professor and research of this place.
Okay, thank you. That's great. And also for your information, my favorite color is also blue, so team blue here. Okay, so what does geotechnical earthquake engineering involves? In general, the subject of this is understanding how soil behaves and behaves differently under dynamic loading. Some, we will see later, some soils lose strength as they are exposed to dynamic and cyclic loading, others actually increase strength. But in general, being able to understand how it behaves, it's something that is key for us to design infrastructure and making sure that we don't have, we are not introducing failures when an earthquake happens. And there are a number of earthquake-induced hazards that we will cover. The most obvious one is ground shaking. That's simply the additional inertial loading that is that our structures are exposed to when an earthquake happens, and has devastating effects through a number of earthquakes. Here I'm showing the two images from the 6.9 Loma Prieta earthquake that happened in 1989 in Bay Area in California. And although the size was not very high, as we will see later, because of several decisions in structural design, as well as some peculiarities with how the seismic waves were amplified, led to extensive damage. And more recently, into 2023, we had the Karhamaras earthquakes in Turkey, which again, because of lack of standards in Turkey and also the very large size of the earthquake, they caused extensive damage with, I think, more than 100,000 injured people. And in this class, I mean, in later lectures, we'll see how the near surface layers and the geotechnical layers affect ground shaking. So here I'm showing a map from San Francisco Bay Area, and in particular we can focus into these two islands. This is the Yerba Buena Island, and this is the Treasure Island. Yerba Buena is a natural island that is a rock outcrop, so very stiff material, whereas the Treasure Island is it was built. It's an artificial island that was built by man-made deposits through hydraulic fill, and there were two stations that recorded the Loma Prieta earthquake. One shown here in the Yerba Buena Island, and one in the Treasure Island. And here we can see the recordings that we have. I think this is in the east-west component in the horizontal direction. And we can see that despite how close these two stations are, where we would expect very similar shaking, we experience significantly higher level of shaking in the Treasure Island. And the reason for that is because the material is a lot softer. So during shaking, the CR modules will see reduced significantly, and that causes seismic waves to be trapped in the near surface and then reflected up and down, increasing the level of shaking. So this is one of the things that we hopefully at the end of the class we will be able to have a better understanding of. Earthquakes also lead to bearing capacity failure, and that's a combination of the structures not being properly sized for the additional loading that they experience during earthquakes, and in particular the eccentric forces that they experience, because now you don't have all of the bearing pressures applied uniformly to the base of the building, but rather on one side, and that increases the stresses at that particular region, causing the soil to fail, as well as we will see how the strength of the material may degrade during cyclic loading, because the water pressure will increase if we consider undrained shear behavior, and leading again to building collapse. Landslides are also a fairly frequent hazard produced by earthquakes. And again, for the same two reasons, the additional loading that a slope may experience, causing it to fail, especially if it's during static forces, it's already very close to the shear strength imposed. But also because the material is relaxing. And also in areas where you have like rock outcrop, you can have rock falls, which again may have devastating effects. Another subject that we will spend a lot of time actually would be liquefaction. That primarily is related to cohesionless soils. So soils where the strength is primarily described through friction angle. And if this soil is in a loose state where shear deformation will cause it to compact, if this shear deformation and this cyclic loading is happening very fast, if there is any water in between the grains, it's not allowed to escape. So as the soil is trying to compact, essentially, instead of the volume changing, is the pore pressure that is increasing. And since the pore pressure is increasing, effective shear stress is less. And that essentially makes one grain to float relative to the other and fully lose shear strength. And then it's a state where the sand or cohesionless soils behave like soup with no shear strength. And if you have a heavy object above a layer that had liquefied, it will sink. And if you have an object whose density is less than that of the surrounding soil, will actually raise to the surface. So during liquefaction, it's not uncommon to see manholes and other pipes being raised to the surface. Also, if you have a gentle slope and you have that layer, there is no resistance in holding whatever material is above to stay in place, and so you have massive landslides and lateral spreads. And if this video plays. So this was from the Indonesia Palu earthquake in 2018, I believe. And you can see doesn't play on my screen, but you can see essentially the entire house and soil underneath sliding with no resistance, even in a very gentle slope, because the soil underneath has liquefied, and so there is nothing holding it back. Another hazard that is caused by earthquake is fault rupture. So to have an earthquake of the two sides of the fault need to move relative to each other. But if that happens at depth, we don't feel the immediate effect of that. We just feel the consequence of that, which is ground shaking. However, for large earthquakes, the rupture is so big that it actually is intersecting the surface, or it's very close to the surface where we have man-made infrastructure. And this is causing an additional demand to structures that are very close to active faults. This is the dam. This is an image from the CIE earthquake in 2001. And you can essentially what happened is that this dam is intersecting the CIE fault, and this side of the fault actually uplifted. That was a reverse fault. And obviously, no man-made structure is able to withstand that size of loading, and so the dam collapsed. This is a historic photo from the Bora Peak earthquake, and this is again a case where the fault ruptured to the surface, and you can see all of the cracks that it produced and the road that it damaged as one side slid relative to the other. But as engineers, we can be clever about it, and also, like, one of the things that we want to be able to understand, to figure out through this course is, if this is to happen, what solutions can we propose to avoid it? For example, for liquefaction, we can think how we can densify the soil or how we can add drains so that pore pressure doesn't increase. Here, this is the Trans-Alaska pipeline that is crossing the Denali Fault. And because they knew that this pipeline will intersect the fault, and if an earthquake happens, there is a high likelihood that one side will slide relative to the other. What they end up doing is, although this is a buried pipeline for most of its length, in the fault crossing, they brought the pipeline to the surface and they put it on sliders. So even if the ground is to slide relative to each other, the pipeline can stay intact and not connected to the ground. And in 2002, when the Denali earthquake happened, it actually showed that this solution was effective and it avoided damaging the pipeline. Through earthquakes, we can also produce tsunamis. This is related to fault rupture. This is when you have fault rupture, but it happens to be under a large body of water, where this deformation that we saw, such as the one from the CIE earthquake, will actually make this body of water to move, and that will create waves. And we had a number of devastating earthquakes that produced tsunamis recently, such as the 2004 Sumatra earthquake and the most recent 2011 Tohoku earthquake. That's it in terms of introduction. Are there any questions or anything to discuss? Yes.
When there is a rupture, then the whole fault like displaces with each other. On the surface on which it has to slide, doesn't it rupture that surface itself?
It does rupture itself, the surface itself. So, like, so for example, these cracks were produced by. Actually, I have also a video here, so let's see if we can play it. This was from the recent Myanmar earthquake, and if I play it back, you see, so the rupture is here, and you see at 10 seconds how the one side. Sorry, it's not. Thank you. Okay. So the rupture, the fault is more or less parallel to this wall, and you can see that as the earthquake is happening, this side will move relative to this side. So the camera is stationed on this side of the fault, so you don't see that size of the fault moving, and you see the opposite here. And another thing that is interesting in this video to see is that you see, like if I started earlier, you see the ground shaking arriving before the surface fault displacement. And that happens because one way that you can think of an earthquake is like a zipper, where you start unzipping from one point and then you propagate along the fault. So you will have deformation when the rupture reaches that location where your structure is, but the seismic waves can often travel a lot faster than the rupture, so they will reach faster than the ground deformation itself. Is this helping with the question? Yeah. Any other questions? Okay. So earthquakes are related to tectonics and plate boundaries. And if we see, for example, even so, this is the earthquakes that happen within the past 24 hours that are magnitude 2.5 and above, and we'll see the majority of them is located along the boundaries of the tectonic plates. But we can also see that there are earthquakes that happen inside the boundaries. So in general, we categorize earthquakes into three main groups. We have active crustal earthquakes. Those are earthquakes that happen in the regular faults that are in around transformation zones, such as the faults that we have in California. Then we have subduction zone earthquakes. Those are larger size earthquakes and are located in subduction zones where we have two tectonic plates converging relative to each other. But we also see we have earthquakes that are away from. Sorry, again, you don't see. I apologize. Okay. So these are the magnitude 2.5 earthquakes that happen within the last 24 hours. And we can also see, change it, like the 2.5, the earthquakes that are magnitude 2.5 and above that happen within the last 30 days. And what we can observe is that most of them are concentrated around the boundaries of tectonic plates, but we also have a number of earthquakes that are located away from them, so in the middle of tectonic plates. And as I said earlier, we tend to categorize earthquakes into three groups. Those were, now if we go back to the presentation. We have the earthquakes that happen along plate boundaries where the two plates are converging with each other, and those are the subduction zones, and we call those subduction zone earthquakes. We also have earthquakes that happen along plate boundaries where the one plate is moving relative to each other, and that are the active crustal earthquakes. And we also have the earthquakes that are in the middle of plate boundaries, and we call these stable continental region earthquakes. And we distinguish these earthquakes into these three groups because they tend to behave differently. So when we want to build models or group them together to understand how they behave, it's typically easier if we follow these groups. So one question that someone may ask is, why do the tectonic plates try to move relative to each other, and in that creating earthquakes. From like maybe even from elementary school, we learn about the plate tectonics and the structure of the earth with the crust, the mantle and the core, and that the temperature is increasing as we go deeper. So as the temperature is increasing, that essentially means like for the same material, it's on a less dense state, and so it wants to flow upwards. You can think of it like different types of fluids. And so because the temperature is higher at the center of the Earth, the material that is there wants to flow upwards, and that is creating convection currents, which once they reach the Earth's crust, they cool down and then they sink back. And as these convection currents are sliding or are moving along the Earth crust, they are actually, because they are viscous, they are trying to drag together the Earth crust with them, and that is what is causing the different directions between the plates, and it's causing them to either collide or pull apart in certain regions. And through those mechanics, there are three main plate boundaries that we have. Those are the subduction zone plate boundaries, where we have two plates converging with each other, causing subduction zone earthquakes. We have the mid-oceanic ridges. This is where new crust is generated because the two plate boundaries are the two plates are being pulled away from each other, and so you are forming a gap, and there is the opportunity for new material to rise there and cool down and form new crust. And then you have transform fault zones, which is the region that is between two mid-oceanic ridges. So if you have two mid-oceanic ridges that are offset relative to each other, you have regions where one plate is moving one way and the other plate is moving the opposite way. So that is causing friction and shear between them, and that is what is causing the transfault fault zones. And a classic example of that is in the US is the San Andreas fault, or in Europe is and in Asia is the Dead Sea fault that caused the recent earthquake in Turkey. Any questions about the plate tectonics and mechanics? So that describes how plates are moving relative to each other in a macro scale, but in a more microscopic scale, we have individual faults. And there are three types of faults that we get that are associated with those three plate boundaries. We have strike slip faults, which is when the two sides of the fault are sliding, or the primary movement is like horizontal sliding of each other. We have normal faults, and those exist in extensional environments where the two sides are moving away from each other, creating a scarp. And we have reverse faults where the two sides are pushing against each other, so that's in compression environments, and this is creating a reverse fault. And depending on the angle, if this is a very oblique fault, so a very small deep angle, those are also called thrust faults, and those are the ones that produce typically the largest earthquakes. And to describe the geometry of the fault and the movement, we have the fault plane. That's the plane that defines the discontinuity between the two sides of the fault. We have the strike, which is like the projection of the fault plane on the surface. And the angle of the strike relative to the north is what we call the azimuth angle. And the dip angle is the angle of the fault plane relative to the horizontal plane. So that defines the fault geometry. And using the rake angle, which is, no, we don't have a board here. This is the angle of the, if you were to think of a vector on the fault plane that is aligned with the direction of the movement, and zero being zero angle meaning horizontal display, horizontal, and 90 degrees being pointing down along the fault plane, that will be the rake angle. So a rake angle of 0 would correspond to strike slip fault. A rake angle of 90 degrees is a reverse fault, and a rake angle of 270 is a normal fault. And maybe two more terms that are useful to be aware of as you go through literature in this area is we have the what we call hanging wall and foot wall. These are used to describe the two sides of the fault for deep slip fault planes. A hanging wall is the block that is above the fault plane, and foot wall is the block that is below the foot plane. And one way to remember it is this comes from mining actually. So hanging wall is the wall, like if you were a miner and you are like digging along the fault plane to like find gold or silver or whatever is typically concentrated there. Hanging wall is the wall where you would hang your lantern to excavate, and foot wall is where your foot are stepping on. So that's the block underneath you. To bring it a little bit closer to home, the northern eastern US typically is described as low to moderate, has lower to moderate seismicity as compared to other regions in the US, such as the West Coast or Alaska. But despite that, this is studying earthquakes in northern eastern US is still important because there has been a number of historical earthquakes that have caused widespread damage. And as an example, don't know, maybe this table is too small, but within the last 300 years, we had about 500 earthquakes that are magnitude 5 and above, and some of them caused damage to infrastructure. We will see through this class, one of the reasons that we had widespread damage is because we don't have high seismicity here, the quality of the rock is actually very high. So there are a lot of cracks. And that means that there is very little attenuation or scattering as the seismic waves propagate. And so even when we have a small earthquake, the shaking from that earthquake can propagate and don't lose a lot of amount of energy many kilometers away and be felt or cause damage. And that's an example, like the Charlevoix seismic zone, that's the zone that is between Canada and Maine. And I think in 1663, it caused a magnitude 7.5, and that earthquake was felt throughout the East Coast, causing damage to chimneys and structures in Massachusetts and in Boston, for example, even if it's like hundreds of kilometers away, which you wouldn't experience for an earthquake of similar size in California. It will only be confined in like few hundred kilometers. Maybe the last thing I want to cover today, and then we can go through some questions, or otherwise we can finish early. The different types of seismic waves that we have. The two main groups are the body waves and the surface waves. Do you have a question? Yes, please.
What is the difference, basic fundamental difference? Is the discontinuity is the surface, which, because of it, there is less attenuation.
Yes, but that, so, like, you can think like if you were trying to, I don't know, as you shear along the fold, you have deformation there, but you are also creating micro cracks, not only at the surface, but throughout the crust in areas with high seismicity. And if you have seismic waves traveling through the crust, those cracks will close and open, and in general, they will dissipate energy because there is friction on these sides. And that is what, and so energy is dissipated through heat and through like sliding on these cracks. And so the seismic waves are not like, they lose energy, and their amplitude is decreasing much faster as they travel away from the epicenter of the fault.
Cracks are west coast,
Yes.
and they are more solid, right?
Exactly, yes. And that's, so here we have like granite, which has like a shear wave velocity of 2,000 to 3,000 meters per second. And it's a much stiffer rock, and also it hasn't been sheared because the seismicity is very low. So when you have an earthquake, that will not happen very often, seismic waves will travel longer. Whereas in the west coast, you have, I don't know, a magnitude 3 at least, I don't know, every other day. So that will cause a lot more shearing and cracking in the crust that will increase the attenuation. Yes.
But how do we quantify the crack density in this area as compared to the visual area? Because then, like, we say that, yeah, cracks are here more, that's why dissipation problem. But how do we exactly quantify? Because it's very difficult to quantify the crack density in the particular region.
So when we will go through, like, I think so that's actually part related to the research that I'm doing. So you can see that effect, first of all, empirically. Like if you have an earthquake recorded here, you will, or let me take a step back. It's not that you will define this not macroscopically, but over larger scales. And we have like parameter that is called quality factor that is describing the attenuation, and that essentially translates to, like, if you were to plot the amplitude of ground motion as a function of distance, how fast that slope decays has to do with that quality factor. So the higher the quality factor, meaning the more intact the material is, that slope will remain flatter. The smaller the quality factor, that slope will decay, or the slope will be higher, so the ground motion will decay faster. And so if you were to record an earthquake here, you will be able to measure noticeable amplitudes even at many kilometers away, whereas in the west coast, for the same size earthquake, the ground motion will decay a lot faster.
That means the crack, this can be considered one of the theory explaining this empirical phenomena that we observe here and here.
Yes.
So there can be another reason also, like density of soil may be different and other things, or rocks or something can lead to the difference in attenuation.
It correct. So those typically have smaller effects. That's why it's not the primary reason. But yes, changes like here is more igneous rock. So like whereas in the west coast is more like transformed rocks. And metamorphic rocks. And those have, and the igneous rocks here have higher density. But again, all of them are related with each other, right? Because if they have higher shear wave velocity, that means they have like higher shear modulus and higher strength. Yes. You can also like numerically, it's also a way to see that effect by running simulations where you can have idealized cases and you can like isolate the effects of like shear wave velocity versus quality of rocks and so on. Any other questions? Or do you have any other questions or? Okay. Yes. Any other questions? Okay, then for the seismic waves, there are the primary waves that we have are the body waves. That are the waves that are traveling through the bulk of the crust, and we distinguish them into P waves, which are waves that are generated by compression and extension, and S waves that are where the a sense of movement is shear. So P waves, also stands from primary waves, and those are the first waves that we typically detect. And that's because they travel much faster compared to the S waves. That's because most materials exert higher resistance in compression and extension versus shearing, and that translates to higher velocity, higher compression velocity as opposed to shear wave velocity. Also, one important distinction between these two is that P waves can travel through fluids, so they can travel through the outer layer of the core, whereas S waves can only travel through solids. So there are certain areas where you don't see direct S waves observations, and that's because those paths would intersect the outer layer of the outer core, and S waves will not be able to travel through. And then these waves, together with the free surface, can interact and create different modes, which we call surface waves. The main two groups there are the Rayleigh waves. That comes by the interaction between P and SV waves. So SV waves are S waves where the shear or the displacement is happening transverse to the direction of propagation, but on the vertical plane. So we have SV and SH. SH are S waves, where again the deformation is happening transverse to the direction of propagation, but it's on the horizontal plane. So the combination of PSVA waves and the free surface is creating Rayleigh waves, and that has a retrograde sense of motion, and that motion is also reducing as a function of depth, so they are more noticeable near the surface. And we have low waves, which are caused by the interaction of SH waves, and when we have a sedimentary layer, where we have a very soft layer underneath above a stiffer layer, where SV waves are trapped and move between the top and the bottom, creating a sense of motion that is transverse to the direction of propagation, but the amplitude is decreasing also with depth. One more important thing to keep in mind about these two types of waves is that surface waves attenuate a lot slower compared to body waves, and that has to do with the fact that body waves travel through 3D space, whereas surface waves travel through on the surface, so on a 2D plane. And so for body waves, the attenuation is proportional to R cube, whereas for surface waves is proportional to r squared, where r is the distance from the hypocenter. So that's what I have prepared for the first lecture. Is there anything that you would like to ask or anything to discuss? Or online if there are any questions? Okay. Then I would say that's it for today.